working now. Okay, thank you very much for waiting. So welcome back to the UniKORN seminars. This is one of the Frontiers seminars, and we're very happy to have with us Georg Enzian. Am I saying your surname correct, actually?
Pretty good, yeah.
Okay, I'll go with that. And just before we start, today we have some announcement for the Born Network. We have the Professor Christian Dolakia is recruiting. I'm sorry, I'm going to butcher that name as well. But they have some really interesting opportunities so feel free to get in touch with them if you're interested. We then have our talk by Georg and a quick question session afterwards. And just again, a reminder to everyone, if you have any announcements about paper publications or exciting news that you want to share with us, send us an email and we put it on the UniKORN or the Born Network website, and we can also put it on the Twitter account, so for some publicity for you. Okay, so now let's go ahead with today's talk, and we're very excited to have Georg with us. And Georg did his PhD. He started off at the University of Bonn in Germany, and then he did his PhD at the University of Oxford with Michael Vanner and Ian Wamsley on Brillouin optomechanics. And he's now just started a postdoc at the Niels Bohr Institute in Copenhagen in the group of Eugene Polczyk. And Georg is going to talk to us about Brillouin optomechanics. So please, Georg, take it away.
Yeah, thank you very much for the introduction and for this opportunity to talk on this platform. It's quite nice how you join forces in the UK to make optomechanics be perceived. And yeah, let me share my screen. Can you see this?
Yeah, that looks good.
Okay. Yeah, so I'm going to talk about the work I did during my PhD at the University of Oxford with Michael Vanner and Ian Wamsley on Brillouin cavity optomechanics with brain gallery resonators. And these efforts are now being continued at Imperial College, where Michael just moved with his group. So why does this not work? Yeah. So I guess most of you are very much aware what we're dealing with here with quantum optomechanics. So we're talking about the control of the motion of mechanical oscillators using light, and the canonical coupling is in this kind of Fabry-Perot cavity, or by radiation pressure. You couple the photon number in a cavity to the displacement of a suspended mirror and variations thereof. And in the Brillouin case, it works slightly different. But what I find particularly intriguing about our field of study is that it has both strong links to applications like quantum memory, transducers, or force sensors, as well as an exciting outlook towards fundamentals like studying quantum mechanics at a macroscopic scale, or decoherence testing collapse models, or maybe in the future also the quantum to gravity interface. So how can you cook up an optomechanics experiment? There's of course many different approaches, but I will just list here a couple of desirable ingredients. So first of all, high mechanical frequency is a nice to have if you want to get close to the quantum ground state with standard cryogenic equipment. Then you would like to have strong optomechanical coupling so that your coherent timescales are shorter than the dissipation in the system. And also what's nice to have is low optical absorption, low mechanical decoherence, high optical collection efficiency, and a good separability of the signal from the pump, which can be challenging in low frequency systems, for example. So in Brillouin optomechanics, we are dealing with the interaction of optical waves traversing through a dielectric material and coupling to sound waves in the material via electrostriction. And on the other side of the coin, the sound waves in the medium affect the light traversing through it by photoelasticity. And here's a little animation where you see light waves going with slightly different wavelengths from left to right, right to left, in opposite directions. And the intensity of the electric field here, you can see that this bead node is moving at a small speed, and you can imagine that this, if this detuning of the light waves is chosen correctly, then this bead node will travel at the speed of sound, and in this case, you get the Brillouin interaction. Oops, yeah. So we are doing these Brillouin experiments in whispering gallery mode resonators, and here's just a couple of examples of the typical modes, like mechanical modes that you find in whispering gallery mode resonators of the acoustic kind. So the acoustic waves are guided by the whispering gallery structure, and you get Rayleigh waves, kind of transverse displacement, transverse waves in the polar direction of the resonator, and longitudinal waves. And these longitudinal waves have the strongest interaction for the Brillouin coupling. So this is how we chose the longitudinal or pseudo-longitudinal, actually, wave component for our studies here. And this is just some mode profiles of the displacement field. And this is roughly how the geometry looks. So there is a resonator of the order of 1 millimeter diameter with a little bulge that guides both light waves and sound waves, and they are spatially overlapping. So in order to make this Brillouin interaction usable, there is phase matching requirements that you have to fulfill. And in a case of a waveguide, these conditions are we have a flat density of states, and Brillouin scattering, so to say, is always automatically phase matched in this scenario. So you can imagine that you were pumping in the forwards direction, and the blue lines here are the sketch of the acoustic dispersion relation, and you will get an intersection here with the backwards optical dispersion. And in this case, you would naturally get the Stokes process winning the race, so to say, and this is also what will lead to stimulated Brillouin scattering, which is a very common nonlinear optical effect. So this basically occurs. This is equivalent to the optical bead node traveling at the speed of sound here in the medium. So now, when you consider the same situation in a cavity, like a whispering gallery mode cavity, the periodic boundary conditions make this a discrete problem, and now you have to basically find this triply resonant case where the optical resonances, like a pair of optical resonances, is detuned by the Brillouin shift of the medium, and where the azimuthal mode numbers match up, so that the sum of the pump and anti-Stokes resonances. So this is in the anti-Stokes scattering case, which is attenuating, which we have used for some studies. In this scenario, you have the sum of these azimuthal mode numbers being equal to the acoustic mode number, and then the coupling rate is just determined by this triple mode overlap and the electrostrictive response of the material, which is normally in the same ballpark for most common transparent materials. And this, it's given by essentially the photoelastic response and the refractive index. So you get in our scenario three wave mixing Hamiltonian of this kind, with a pump, an anti-Stokes, and a mechanical mode operator. And you can think of it like this. So you have your pair of optical cavity resonances of different transverse character. So it's not equal to the FSR, but it's different spatial modes. And this is to break the symmetry between the Stokes and the anti-Stokes scattering. And for these experiments, exploring the system, we have often pumped on the red mode and looked for upconversion scattering into the this orange cavity mode, which is called anti-Stokes mode. And essentially, then you can either pump on the red or on the bluer resonance, and then you get either a beam splitter type or a two-mode squeezing type Hamiltonian of this kind between the anti-Stokes cavity resonance and the mechanical resonance. So let's first look into results that was observation of strong coupling in this system. So strong coupling has some history in quantum science. For example, these beautiful experiments at Caltech showing strong coupling in cavity QED, and then also the strong coupling of a superconducting qubit to a microwave field. And in these cases, the coupling rate exceeds the damping rate of both electromagnetic and matter decay rates. And in optomechanics, this regime was first observed in Vienna in 2009, and then another nice parameter regime is the quantum coherent coupling regime, where the coupling rate not only exceeds the damping rates, but also the mechanical decoherence rate, in which case you get a coherent exchange of excitation between the degrees of freedom. So the setup that we used looked like this. We would typically pump the cavity in the forwards direction with a 1550 nanometer pump laser, and would then look for these optical resonance pairs and observe a backscattered light, which is then blue shifted, and do a heterodyne detection of these the scattered light. And this is an image of the resonator. So it's a fused silica micro rod that is made with a laser lathe by our collaborators at NPL in Pascal Delhai's group. And we would couple to this bulge here with tapered fiber. And the typical dimensions are of the order of a millimeter. So for this experiment, we used a 700 micron diameter resonator. And then what you would find is this is increasing pump power here for a particularly nice mode pair. So you would find a single scattering peak at low pump power, and then so this is the built-up power. This would be at an input power of only a few milliwatts because of the very large optical quality factor. And then as you would increase the power, you would see a double peak structure appear. And this is in fact the typical voided crossing signature. So you would get these hybrid modes of light and sound. And the typical situation is that these bifurcation point in the spectrum, and in our experiment there is an additional process going on that actually not only is the coupling rate increasing, but also the detuning is changing. So you get a kind of combination of an avoided crossing plot and a bifurcation plot at the same time, so to say, as both these parameters are simultaneously changing. And you can understand that from the fact that there is the optical Kerr effect in the medium simultaneously going on, and it's leading to self and cross phase modulation of the optical resonances, as well as a thermal refractive effect of the mode volume warming up by the absorption of dust on the surface of the resonator. So it's not clear how the relative contributions of these effects are not clear, but they both would lead to a linear detuning change with pump power here. And this is what we observed in the experiment. So here you see the coupling rate achieved versus the intracavity pump power. And just to say that this crossing here is achieved for a few milliwatts of input power only, making this quite interesting observation. And the bare coupling rate in this case was around 400 hertz. So 3.25 times stronger than the hybrid decay rate, which is the purple line here. Yeah, so the second result I'm going to talk about is the single-phonon addition and subtraction to a mechanical thermal state. So when you add or subtract a single quantum to a thermal state, then you will find, when you calculate it, and I found this surprising at first, is that in both cases you get an approximate doubling of the mean phonon number, and you can get an intuitive understanding of this, that when you do this operation, you're updating a knowledge and so to say, when you see a click, you have information about that the oscillator is currently at a high excursion, and then you can understand this effect from the redistribution of the phonon number distribution, or in this case the photon number distribution, which was first studied in these two works in 2007. So in our system, we would implement it in the following way. We would either pump the system on the blue resonance of this optical mode pair, or on the red resonance of this optical mode pair, and would scatter into the respective other mode of the cavity. And then we would implement this way either an addition operation or a subtraction operation to the mechanics. And a way to think about it is that, let's look at the beam splitter case first. So you have an input density operator, and you put it through a beam splitter and observe a photo count here in this port. And then you can ask, well, what kind of measurement operator would be represented by this case to give you a certain output density operator here. And then when you put in a beam splitter, a Hamiltonian with some characteristic time scale, you find that approximately that resembles when you do the let the operators act here to the right and to the left, that the measurement operator this corresponds to is in fact proportional to the phonon annihilation operator, and a similar argument leads to the addition operator in the other case. So so then this is a kind of pictorial a sketch of the experiment. So you have an optical cavity mode A and a mechanical cavity mode B, and if you assume that there's a unitary evolution between these modes, then outside the cavity you have a field C on which you do photo counting, and then we're measuring the effect of this operation with optical heterodyne detection. And when you do the maths, you're basically interested in the variance of the light in the cavity mode A as a proxy for the mechanical mechanical phonon number, so the energy in the oscillator. And when you do these steps, it basically boils down to that you have to calculate a correlation function of the optical cavity field in order to know what the expected variance of your optical cavity field becomes upon performing this click operation. So the experimental setup is similar to what I described before, only that now we are splitting the output light here, and we have to filter spectrally the light from spurious pump light that you will always get from elastic scattering. We're using fiber Perot filters, which we tune accordingly to then perform the subtraction and addition operations with a single-photon avalanche diode. How is it time-wise? Okay.
You're still good.
Okay. Yeah, and then essentially we record with a balanced photodetector in a heterodyne scheme the scattered light and herald this recording with observation of the photo count here. And then what you observe is so plotted here is the variance of that the heterodyne detection scheme measures versus the time away from the photo count for the addition case and for the subtraction case. And you can see that at the time of the photo count, you get this approximate doubling of the variance here, and then you get this decay back to kind of an equilibrium scattering situation here, which contains the decay rates of the cavity. So you can calculate it like, and then you find essentially this approximate doubling in both cases with the cavity optical cavity decay rate kappa and the mechanical decay rate gamma imprinted onto the light field. Yeah, and maybe a little outlook. So we did this addition and subtraction experiment with a crystalline cavity because amorphous material like fused silica has a much more two-level system damping, and so we chose to explore crystalline materials. And you probably aware of these very impressive cavities of the bulk phonon cavities, the Galliou and Renninger works, for example, for microwave probing and optical probing, where QF products were in this range of 10 to the 18, and this was observed with crystalline materials at cryogenic temperatures. So we are looking into doing crystalline Brillouin cavity optomechanics and whispering gallery mode resonators at cryogenic temperatures. And then the question arises, can you actually find an elastically isotropic crystalline material? And the answer is no, as you basically always get a dependence of the speed of sound of the direction. But it turns out that there is a material which is quite attractive, which is a barium fluoride, where this dependence is quite weak, of the order of 10 to the minus 5 only. So here plotted is the directional dependence of the acoustic phase velocity, and when you plot it versus the angle, so basically when you make a whispering gallery out of the material, you would not like it if your Brillouin shift was vastly changing around the perimeter of the structure. So this material has a very attractive properties, also very low optical absorption. So we are now looking into exploring this further. And here is a picture of this barium fluoride rod, which has 3 bulges written into it, and this was done in Australia by our collaborators, with the main efforts being done by Jiří Janosek, and this was done with a diamond lathe. So you cannot afford to do it with a laser lathe because you would melt up the structure on the surface and make an amorphous layer. So yeah, going back to the cooking up of the optomechanics experiment, we have ticked most of these boxes and currently looking into pushing down the mechanical decoherence. With that, I would like to close. Thank you for your attention.
Thank you very much, Georg, for a really nice talk. I especially like the smorgasbord picture at the end. So if everyone could just unmute yourselves for 1 second, and we'll all give Georg a round of applause. Thank you, Georg. Okay, so now we have some time for questions. So if you have a question, please raise your hand, and I'll try and keep an eye on that. And we'll also keep an eye on the YouTube chat. We currently have no questions there. So I can start off with a very naive theorist question. I'll turn on my camera as well. So when you mentioned the coupling strength that you had for these automechanical systems, you mentioned that it was called the bare coupling. And I was just wondering what the definition of a bare coupling as opposed to just a coupling is, and if there's anything to consider there.
Right. So the Hamiltonian for the Brillouin interaction is slightly different than for conventional optomechanics, where you typically have only two oscillators involved. So you have one optical cavity mode and one mechanical mode that you're typically considering, and then you linearize the interaction, right? And you basically from that get a coupling rate G. And in this case, what I call the bare coupling rate, or the single photon coupling rate, is the G naught that is in front of this trilinear Hamiltonian. And then basically when you do the parametric approximation for one of these optical fields that you pump on and replace it by a kind of coherent amplitude, then you would get this enhanced coupling rate, which is enhanced by the photon number in that resonance of the cavity. So this is just how it's connected.
Okay, fantastic, thank you. I think we have a question from Ignacio.
Thank you for the nice talk. So I was curious about this mechanical decoherence that you're working now. So you mentioned on the slide this FQ product of 10 to the 18 that is very impressive. Is that at low temperature, I assume? And probably
yes, this was done at low temperatures in America, yeah.
And so in this situation, basically the mechanical dissipation, I would imagine that it's from phonon scattering, not from intrinsic processes of the material, or is there something else to consider?
I'm not sure if this number of 10 to the 18 is only limited by the intrinsic kind of 3 phonon interaction in the material, or if there is some other effects that might have to do with the purity, or but I'm not sure.
I see. But then to achieve what you want, you just need to repeat everything at very low temperature, or is there something else?
I think it's not. Yeah, it's not as simple as that. So we're thinking now that there's basically 3 contributions to the 3 main contributions to the sampling rate, and one is the material absorption itself, which at room temperature is quite dominant, because at room temperature at these frequencies, the Brillouin line width is of the order of 20 megahertz, and we observed damping rates of the order of 30 megahertz. But then we think that there is a contribution of diffraction from the surface, that the surface actually radiates waves into the support, like transverse waves, and we are currently studying this. And also it might be that as we are going at a very glancing angle at the surface, that surface roughness will lead to scattering loss into the support of the structure.
I see.
So we don't believe that we are straight away going to get similar QF products when we cool it down.
So
But,
one of the things you mentioned about the diffraction somehow probably has to do with the shape of this hump, no?
Yes. So this is essentially what we're currently studying.
Of changing that? Can you engineer the way this shape is?
That is an open question, actually. Yes. So we are thinking about whether you can shape the structure slightly differently in order to minimize this loss.
Because there are these things by Tobar, you know, the work by Tobar on quartz resonators. I think if this has like a good shape, probably you're getting rid of that, no? Then...
yes, but we also think that this quasi-longitudinal waves would have the strongest Brillouin coupling. They actually suffer from a certain loss that you get from the coupling of transverse and longitudinal component at the surface. And that's why you get radiation of transverse waves into the center. This is what we think, and this has not been appreciated before in the literature. So
that's really interesting.
Basically, the pseudo-longitudinal waves have the strongest Brillouin interaction, but they might have some higher damping.
Thank you. Thank you very much.
All right, thank you. We have another question from Edward. Can you hear us, Edward? We sadly can't hear you just yet, or I can't.
Maybe you can type the question. Or...
Yes, if you can type the question in the chat, I can read it out. Okay.
I can ask a really simple question whilst oh no, fine.
Yeah, so the question is, do I understand correctly that the variance doubles when you subtract a phonon? That is the question. I'm reading it, so it's on the YouTube recording as well.
Yes, that is exactly right. So you get a doubling when you subtract the phonon, and you can well, you can understand that in terms of, for example, I mean, the state that you're operating on is a thermal state, so it has only, you have minimal knowledge of the state. You just know the mean phonon number. So essentially, when you get a scattering click from it, you update your knowledge about the excursion of the oscillator. So this is how I like to think about it. So in fact, yeah, you get a doubling from subtracting.
And then the follow-up question for that is, doesn't this violate energy conservation?
No. No. So you because you're not operating on a number state. So the in which case you would decrease the variance, but because you're operating on a thermal state, you have very little knowledge of the state that you're operating on, and you can really understand it in terms of updating your knowledge. I don't know if that answers the question. That's how I like to think about
I think so. So Edward says thank you in the chat. So Leah, did you have a quick question?
I had a really simple question, which was, you may have already mentioned it. What's the typical optical quality factor of these resonances, and does it matter? Is there an influence if it's particularly narrow line width or not?
Yes, so we have seen line widths below 1 megahertz at optical frequencies of 200 terahertz. So that's larger than 2 times 10 to the 8. But in similar structures, even larger quality factors have been observed in the 10 to the 9 upwards range. And it's certainly so there's a couple of, I mean, there's a couple of factors that limit that, but what's certainly relevant for this system is, of course, the optical absorption, and both silica, so fused silica, which we have used in the first experiment, as well as barium fluoride have, for example, no 2-photon absorption. They have very low optical absorption in general, which makes them attractive, because you don't want to introduce heating when you want to do your optomechanical experiments.
So,
Thanks.
All right, so we're nearing 30 minutes. So I'll just have one more look if there are any more questions. So anyone has another questions, please raise your hand. I don't think so for now. So I'm sure if people have more questions, they can reach out to Georg. Yeah, thank you so much, Georg, again for coming on to giving a seminar. And next week we'll have Alessio Belenkia, who's based in Belfast, give a talk on the theory of optomechanics and thermodynamics, and maybe ties in a little bit to what we had today. So thank you so much, Georg, and please come back next week.
Thank you.
Okay, thank you. Okay, thank you, everyone. So I will now quit the live stream, and we look forward to seeing you again next time.